Thank you, and thanks to the organizers for the invitation. So I'll talk about the spectral properties of random perturbation Toeplitz matrices with finite symbols. So I'll explain what do you mean. So there should be, sorry, it's a typo, should be finite symbol, not matrices. Sorry about that. Anyway, so this is based on joint works with Elliott, Packet, and Ofer Zaitoni. So I'll start with an example. So you start with this very simple matrix. You have zeros on the diagonal and 1 on the first super diagonal, and the rest of the entries are all 0. Okay? So since this is an upper triangular matrix with zeros on its diagonal, so we know that all its eigenvalues has to be 0. Okay? Now suppose I conjugate this matrix by a unitary matrix on the left and its complex conjugate transpose on its right. So I define this Tn hat, un, Tn, un star, where un is a unitary matrix. Okay? Then we know that the eigenvalues of Tn hat is same as that of Tn. Suppose instead of taking any fixed unitary matrix, suppose you sample a hard unitary matrix, meaning that you sample uniformly at random from a set of all unitary matrices of dimension n. Now you do the same operation. Now you multiply that un on the left and multiply un star on the right and compute diagonals of Tn hat using any mathematical software you like. So once you do that, you'll see that something very interesting happens. So in this example, where we took this Tn, so let me write it down, this example, which I'll come to it again. So we have this Tn, this is our example 1. So Tn looks like this. 0 on the diagonal and 1 on the first super diagonal. The rest are all 0. Okay. So in this particular example, if we now take a hard unitary matrix, conjugate it on the left by it and by its complex transpose on the right, then you see if you do this by Mathematica, you get a completely different picture. So you see that, so this black circle is a unit circle on the complex plane, and you seem to have most of its eigenvalues are very close to the boundary of this unit circle, and there are a few inside. So you start from a matrix which has all its eigenvalues to be 0, and when you do this operation, you get something which is completely different. Is this example clear? Okay. Now, and this is not particular for, this is not anything related to this particular matrix. You can do it, you can repeat this procedure with many different matrices. For example, you can take this Tn. So you have again zeros on the diagonal, 1 on the first super diagonal and 1 on the second super diagonal. Then you get another different picture. So then you get this black limmason, which is the image of the unit circle by this symbol, A lambda is lambda plus lambda square, and all its eigenvalues seem to be close to that black limmason. And again, in this particular example, I will write down the example because I will use it again and again in this talk. 0 on the diagonal, 1 on the first super diagonal, and 1 on the next super diagonal. Rest are all 0. Okay, and you can repeat again. So here I take a different matrix, so which is again of that similar type. It is not upper triangular anymore, but you have 1/2 on the first super diagonal and I on the first sub diagonal, and you get a similar picture. So this is our example 3. So 0 here, 1/2 here, and I here. Okay. And here what you get is a similar picture where this ellipse now, this black ellipse again is the image of the unit circle by this symbol 1/2 lambda plus I lambda inverse. And these green dots that I have dotted, that I plotted here, is basically the eigenvalues of the Tn. So you again see that if you conjugate by a hard unitary matrix on the left and its complex conjugate transpose on the right, you get a completely different picture than what you started with. Okay. So in this talk, our goal would be to try to model this phenomenon and try to see what you can understand of that model. Okay. So you can think that what is really happening is that when you're sampling this hard unitary matrix, because some rounding error or some other stuff, what you're really sampling is this un plus some small error matrix. Okay? And then if you do a little bit of algebra, then what you are really computing is the eigenvalues of Tn hat is basically eigenvalues of Tn plus some noise matrix, which looks like this. So this phenomenon, you can model it as that you are starting with a Toeplitz, so I'll define, okay, starting with this Tn, and then you're adding some very small noise. And then what you're really looking is the spectrum of this additive noisy model. Okay. So then one can try to do is that try to model this En by putting a random matrix. And then one can study this additive random perturbation of this Tn. Okay, so what we know about this random matrices is that suppose you start with a random matrix which has all its integers are IID with 0 mean and finite fourth moment, then the operator norm scales like square root n. Okay, so there are two possible approaches to model this phenomena. So what one can do, try to take this Tn plus add sigma over square root n, where sigma is a parameter, and En is a matrix with IID entries, let's say 0 mean and finite fourth moment. And then what you try to understand is the spectrum of this sum. First you let n go to infinity, then you allow sigma going to 0. This is one possible way you can try to model this phenomenon. Another way what you can do, you can try to look at this sum Tn plus n to the negative gamma En, where gamma is strictly greater than 1/2. So this way what you're adding is really a noise because its spectral norm goes to 0. And in this talk, we'll follow the second approach. We'll take, so what we'll study is the eigenvalues or the spectrum of Tn plus n to the negative gamma En, where gamma is strictly bigger than 1/2, and En will be random matrix with certain assumptions. Sorry, say that again? En is not upper. No, En is not upper. En can be, so we'll see that in most of the cases, En will be a matrix with IID entries, with certain restrictions on the how those entries, how the distributions of those entries look like. Yeah, so Tn will take all these three examples. So it could be upper triangular, it could be non-upper triangular, and so on. But as we'll soon explain, that Tn will have in this particular talk, we'll take Tn to a Toeplitz matrix. So I'll come to that. En need not be symmetric. En could be. So some of our results require that entries are independent, and I believe that some of the results can be modified to allow En to be symmetric. So, but we do not take En to be symmetric to begin with. Okay, so what are the questions that will be interested? So we'll be interested to know what is the bulk of the spectrum look like. So the limit of the bulk of the spectrum. So it means that you look at this empirical measure induced by this eigenvalue. So the lambda is the eigenvalues of this matrix that you're interested in. So you look at this empirical measure of the eigenvalues, and then you want to know what is the limit. And another question that you might be interested in is what is the limit of the random point process that is induced by the outliers. So I'll explain in a minute what do you mean by outliers. Okay, so here, what do I really mean by an outlier? So again, let's go back to this example 1, where this Tn has this nice form that there's 0 on the diagonal and 1 on the first super diagonal, and the rest of the entries are 0. And suppose what I do, I look at this Tn plus En now, where En is 1 over n Gn, and Gn is a complex Geneva matrix, meaning that all its entries are standard complex Gaussian, IID standard complex Gaussian entries. Then then you can try to plot the eigenvalues. So the eigenvalues are in red. As you can see, it is very close to this unit circle, and you can see there are few red dots which is far away from the boundary of this unit circle. So those I call them to be outliers. So as you see from the picture, that most of the eigenvalues of this sum Tn plus En, where En is of this form, will stick to the boundary of this unit circle, and there will be few which will be away from this boundary of this unit circle. So those I call them to be outliers, and one of the goals in this talk will be to explain or at least characterize what are these outliers. And in orange, I just plotted the eigenvalues of Tn hat, where Tn hat is Un, Tn, Un star, and again Un is a Haar unitary. This is done using Mathematica. Okay, and similar things you can do for example, examples 2 and 3. So you get similar picture. So again, these eigenvalues stick to this black limmason, and there are a few which is away from this limiter. And then in this example 3 again, you see that most of this eigenvalue is close to this ellipse, and there are a few which is away from this ellipse. And one thing I would also like to mention that you see that there are no eigenvalues outside this ellipse. So this will be also clear as I go on. There should be no outliers outside these regions with probability tending to 1. Okay, so all these examples that I have described, these 3 examples, they fit into a broader class, which is Toeplitz matrix. So by Toeplitz matrix, I mean that you are given a collection of complex numbers, AIs. So what to do, you put A0 on the main diagonal, A1 on the first super diagonal, A2 on the second super diagonal, and so on and so forth. And similarly, put A -1 on the first subdiagonal, A -2 on the second subdiagonal, and so on and so forth. So this is what is known as Toeplitz matrix. So you can see all these 3 examples, each of the 3 examples fit into this category. So what we really will study here is a spectrum of Tn plus a noise matrix, where Tn is a Toeplitz matrix. Okay? And we'll call this Tn to be banded, finitely banded, if there is a band structure around the main diagonal, meaning that our AIs are 0 if I is too large, if I is very big, or if I is very small. So there is some finite d1 and d2 such that if I1 is greater than I is greater than d1 plus 1, then AI is 0, or I is less than negative d2 plus 1, then it is also 0. And again, these 3 examples fit into that class. Okay, so note that this Tn I can view it as a truncation of an infinite dimensional Toeplitz operator. Okay, so you can think this is n by n truncation or n by n projection of this infinite dimensional Toeplitz operator, and that also comes with this symbol. So I will say that this A, with which you define this matrix Tn, is a symbol associated with this Toeplitz matrix or this Toeplitz operator, where this A is this infinite sum running from negative infinity to infinity, ak lambda to the k. So each Toeplitz matrix comes with its own symbol. So if you give me a symbol, then I can define a Toeplitz matrix. And in this talk, we will be considering T or equivalent Tn, where this is banded. So banded meaning that, as I said, it has a band structure around the main diagonal. So in that particular case, our symbol becomes a finite sum. It runs from minus d2 to d1 ak lambda to the k. So this is a Laurent polynomial. So in these 3 examples, you can see that, check out in our first example, the symbol is just a lambda is lambda. In the second example is a lambda is lambda plus lambda square, and third example is you have this form. So now before I move on to stating the main result, I want to say that there is a connection. What we are doing here, like we are taking this Tn and adding a noise, and we want to study the spectrum of this noisy Toeplitz matrix. It is very well connected to a notion which is very well known in numerical analysis called pseudospectrum. So what is a pseudospectrum? Pseudospectrum is the following. So suppose you start with a matrix and add a noise. Then the pseudospectrum says that what is the worst case scenario that can happen to the spectrum. So this is represented by this. So you look at the spectrum of A plus E, where E is a noise matrix, such that its norm is less than or equal to epsilon. So this pseudospectrum tries to understand how far you can move the spectrum by adding a small noise. And here what we're doing, instead of looking at the worst case scenario, we're looking at a typical case scenario. Because we're adding a random matrix, so basically we're trying to see how far the spectrum moves, or how does the spectrum behave when you add a typical noise matrix. And from this next picture, you can see that they are very well connected. So again, I went back to this second example where this symbol that we have a Toeplitz matrix with symbol a lambda equals lambda plus lambda square. So you have this example. And then you calculate the epsilon pseudospectrum for various choices of epsilon. Okay? And these, on the left panel, what you see is a level sets of those pseudospectrum. And they closely represent or they look like as if you are doing a random perturbation, which is on the right. So these two different approaches are very much similar to each other. So So basically, so let me see. Yeah, so basically what you're doing here, you're looking at the epsilon pseudospectrum. So means that you're looking at the spectrum of A plus E where the norm of E is less than epsilon. Now you take your epsilon to be these values, so these are the level sets of the pseudospectrum. And those shapes looks like as if you are adding this random perturbation. So there you take all possible E's, and then you look at this spectrum, how far your spectrum moves from the, which is here is a 0, it's a point mass at 0, and how far it moves, and this is the level lines that you get out of that. Another question? Yes. Right, E could be any matrix. Yes, so basically this alternate representation also helps. So if you look at now A minus Zi inverse, take its spectral norm, and now you look at all those Z's, so this is equals 1 over epsilon. That will also give you the level sets. So this equivalent representation actually helps you to compute this pseudospectrum. So this is not easy for any general matrix. So there are some, I guess there are some packages or tools that you can use. So I have never personally used that, so I don't know how that package works. So it is not really easy to compute for any given matrix. Okay, so now let me set the first main result in our setup. So we have this Toeplitz matrix. So I'll go over it slowly. So a Toeplitz matrix of dimension n with symbol A, where Tn is banded. Then as I said, it means the symbol is a Laurent polynomial. Okay. Then I take any random matrix En which satisfies these two assumptions. I will come to this in a moment. Then what you can show is that for any gamma greater than 1/2, the empirical distribution of the eigenvalues of Tn plus n to the negative gamma En converges and it has a limit. And the limit is given by the push forward of the uniform measure by the symbol. Okay, so let me explain what it means for these three examples. Okay. So if we go back to this first example, which is very simple, then it means that this empirical law of Tn plus, where Tn is this guy, n to the negative gamma En, where En has certain properties, converges to the uniform distribution on the unit circle. Okay, so if you take this matrix, if you add a noise, where the entries are IID with certain distributions, and if you scale this noise matrix by n to the gamma, where gamma is strictly greater than 1/2, such that its spectral norm that you are adding is going to 0, then the empirical measure of this sum of the eigenvalues of this empirical measure of the eigenvalues of the sum of these two matrices converges to the uniform measure on the unit circle. Okay. Similarly, if you go to the second example, what it does is that this empirical law now converges to the law of u plus u square. So you start with an u, and if your symbol is something, then what you get in the limit is the image of the this uniform measure on the unit circle. Okay. Similarly, for example 3, you have this symbol, so the law becomes now this guy, 1/2 u plus iu inverse, and so on and so forth. Yes. No. So as soon as you're gamma greater than 1/2, you get the same limit. And you can also take gamma approaching 1/2. That is also possible. So I'm setting where gamma is fixed and some quantity greater than 1/2, but it is also possible to let gamma go to 1/2. You'll see the same limit. Okay, so now let's go back to this assumption A. So I said that we need this assumption A. So I need a condition on the Hilbert-Smith norm of this noise matrix, which is same as saying that I need that the second moments of the entries of this matrix is not too large. And I have this order n square sum, so I need that each of the entries of this variance, the variance of each of the entries is order 1. And the second condition is a bit technical. It says that for any matrix which is of not very high norm, if you look at the smallest singular value, this mn plus en, where n is noise matrix, then that smallest singular value cannot be too small with high probability. So this condition is a bit technical, but as I'll explain to you in the next slide, is this slide that there are many such examples where both these assumptions are satisfied for En. So one thing you can start with that En is a matrix with IID entries with finite second moment. So then you can check that, one can check that both the assumptions are satisfied. So in these three examples, if you add a noise matrix whose entries are IID with finite second moment, if you scale by n to the gamma, then you get the limit that I stated. And there are many other examples where all these assumptions, both these assumptions are satisfied. Suppose you take en to be square root n un, where un is Haar unitary, and there are other conditions, like they can also have some inhomogeneous variance profile. It could be a sparse matrix, and there are many other examples. So I just listed some of them. Let me now state some of the earlier results. So there are some earlier results in this direction. So this paper by Gione, Wood, and Zaitoni, they consider this first example where the symbol is just lambda, and they consider this Gaussian perturbation. Then there is improvement by Philip Wood, and there's two other cases considered by Sosten and Vogel. But all of them consider, except this work by Wood, all of them consider under Gaussian perturbation. So what our results tells is that that you can allow your perturbation to be very general. So next, we want to understand how the outliers behave. Okay. So first, as I shown in the pictures, that there are regions where you don't seem to have any eigenvalues of this random perturbation of these Toeplitz matrices. Okay. So what you can show is the following. So suppose again you have a finitely banded Toeplitz matrix, and En is a random matrix with independent entries having just zero mean and unit variance. So you don't need the distributions to be identical, so you just need the entries to be independent having zero mean and unit variance. Then for any gamma greater than 1/2 with probability tending to 1, there are no outliers outside the spectrum of this TA, where T is the limiting Toeplitz operator. So what do you mean by that? So in this particular three examples, you can think that, as I said, that this Tn you can view it as a n by n truncation of an infinite Toeplitz operator. So our T is that infinite Toeplitz operator that comes out naturally from this Tn. So what it says that with probability tending to 1, there are no outliers outside the spectrum of the limiting Toeplitz operator. So it is a very classical result about the spectrum of this any Toeplitz operator, and it has two components. So the first component is the image of the unit circle under this symbol, and the second component is that also Z, which is not in this image, you collect also Z such as the winding number of A minus Z is non-zero. So it has two components. So it has A of S1, and any point in outside A of S1 for which the winding number of the symbol minus Z is non-zero, around 0, those points are also there. Okay, so let me again go back to these three examples. Okay, so before that, let me give you this example. So you have some symbols. So you have this symbol, and then you can compute what are the winding numbers of this curve for this different part of this complex plane. And you can see that these two regions, they have zero winding number. So the spectrum is the collection of all those regions where you see a non-zero quantity. So this is this gray shaded region for this spectrum. So this is the spectrum of this Toeplitz operator, where you have this Toeplitz operator with this particular symbol. Now if we go back to all these three examples, there the spectrum is very nice. So for the first example, where you have this Toeplitz matrix and corresponding Toeplitz operator, the spectrum you can compute, it is just a unit disk. Everything outside unit disk has a zero winding number. Okay. So, and as you see from this example, that the simulation, that there are actually no outliers outside this unit disk. And similarly, if you go to the second example, then everything in this black limaçon has a non-zero winding number, and as you have seen from the simulation, all the eigenvalues are inside that limaçon. And similar thing happens for the third example as well, and the spectrum is the solid ellipse, and all the eigenvalues are inside this solid ellipse. So now once we've understood what are the regions in which outliers can live, now we'll try to understand how the random point process induced by the outliers behave in the limit. So before introducing the result, I need to define a certain notion. So we start with this symbol. So this is Laurent polynomial, this is a finite sum. I have L running from -d2 to d1, or some d2 and d1. So what I do, I multiply this a lambda, I subtract z, and I multiply by lambda to the d2. Now it becomes a polynomial. So now let's lambda 1, lambda 2, lambda d are the roots of the polynomial. They're arranged in the non-increasing order of the moduli. And I denote Rk to be the region where they are exactly, so okay, so again there is a, yeah, no, so it's fine. So I define Rk to be the region where there exactly came in roots which are strictly greater than 1 in moduli. Okay, so I can decompose the whole complex plane in according to how many roots of this polynomial are greater than 1 in moduli. So for example, if I go to this example 2, I have this Limassol. So what one can check is that number of roots greater than, so here both, so this will be region 2, this will be region 1, region 0. So it means here one can show that both the roots, so if we have this Limassol, then our symbol is lambda plus lambda square. So the equation that we are looking at is this quadratic equation, lambda plus lambda square minus z. And one can check that if you are outside this Limassol, then both the roots are greater than 1 in moduli. If you are here, there is exactly one which is greater than 1 and one less than 1, and here both are less than 1. So I can decompose the complement of AS1 into these disjoint parts. And what I will explain in the next slide is that the random point process that you're going to get as the limit also changes in these 3 different regions. Okay, so let me state the result. Okay, so we have this Tn, again the same setup. We have this Tn with finite symbol A, and now we assume this extra condition that the entries of En are complex valued random variables with bounded density. Then what you can show is that if I look at the random point process induced by the outliers of this Tn plus n to the negative gamma En, then they converge weakly to the random point process induced by the zero set of some explicit random analytic function. Okay. And this limiting random analytic function is not universal. It depends on the distribution, and its description differs across these different regions. So it will be different in R1 and R0 and etc. So I'll give an example to illustrate how it differs and what is this explicit random analytic function. And there are some other results for these 2 specific cases where you take either example 1 or example 3. And then if you add this Gaussian perturbation, then the limiting random analytic function is actually a Gaussian analytic function. And then your random point process is the zero set of this Gaussian analytic function. Okay, so let me explain what do we get in this simple example where we have this example 1. Okay. So as I have said that outside this unit disk, you don't see any outliers for this example. So all the outliers will be inside the disk. So what is this random analytic function looks like inside this disk? So it looks like this. So you have this f of z is given by sum of over all integers greater than or equal to 1. Then you have z to the x plus y minus 2. Then you have this sign times exy, where exy is an entry of an infinite dimensional array with distribution same as that of En that you started with. Okay, so you can think that as you are adding this noise matrix En, you can also think it as a truncation of an infinite dimensional array. And the distribution are the same as you started with. So this is this form. Okay. Now if you allow it to be, if you allow the entries to be complex Gaussian, then you can see that it simplifies to this guy, because then the sign doesn't matter, and you just count how many integers x and y will give you x plus y minus 2 equals k. So you collect all of them, and then use the fact that you have Gaussian random variables, so that gives you, that simplifies this form of this function, and it becomes to be this nice hyperbolic Gaussian analytic function. But if we do not allow, if we do not assume it to be Gaussian, then you get a slightly more complicated form like this. Yeah, so here, so if you're inside this unit disk, for this particular example, then the winding number is either -1 or +1, I forget. So like it depends on, like, let's say it's 1 if you're going anti-clockwise. So it depends, so as I'll explain, so it really depends on the winding number. So if the winding number changes, then the form of this analytic function will also change. Okay, so more generally what happens is the following. So now it becomes a more complicated function. So it is some coefficient c, x, and y, where this c depends on the roots of the polynomial that you started with. That comes from your symbol. Then you have this determinant of the submatrices of this infinite dimensional matrix, where you take the submatrices induced by the rows x and columns y, where this x is again function of this little x and little y is function of little x and little y, and x and y has certain dimensions. And this dimension script d is d1 minus d0, where d0 is the number of roots greater than 1. So if I want to rephrase it in terms of this example 1, then what we see is the following. So as I said, our fz for example 1 looks like this. So I have some xy integers, then I have z to the x plus y minus 2, negative 1 x plus y minus 2, and then I have this exy. Okay. So here, note that so this is my Tn, 0 and 1. So d1 is a number of non-zero upper triangular entries that I see here. So here our d1 is 1, and our symbol is just lambda. So the equation is very simple, lambda minus z equals 0, which is equivalent to saying that z is lambda. So if you're inside this unit disk, then there is no roots which are greater than 1. So my d0 is 0. And therefore what you see here that I wrote here, this script d is d1 minus d0 is just 1. So that's why when you look at this determinant, it's just a single entry of that matrix. And you have this sum function, which is some c x y, which is in this case this takes this form. So in general, it would not be a linear in the entries of this noise matrix. So if, for example, if your script is 2, you get a determinant of 2 by 2 submatrices of your matrix, which is definitely not a linear function of the entries of the noise matrix. So it means that even if you started this Gaussian noise matrix, then you might end up with something which is not a Gaussian analytic function. Okay, so in the next few minutes, I'll try to give some ideas about this proof. So since we're trying to understand what are the behavior of these outliers, so we know that outliers in particular are the roots of this determinant. So if the determinant of this sum minus z identity, these are the roots of this determinant. So what you can do is the first step, just expand the determinant. So, and what do you mean by expanding the determinant? It's just a simple exercise. So you have this determinant of this sum of two matrices. So it's just from the definition of the determinant, it is determinant of this Tn minus zi dn. You look at the sum matrix induced by x complement and y complement as rows and columns, and multiply by the determinant of this noise matrix. Look at the sum matrices induced by the complement of the rows here and complement of the columns here. So it just follows from the definition of the determinant. And then you have some sign. This is because how you choose your x and y. So there is nothing fancy here. It just follows from the definition of the determinant. So once you have expanded this determinant, then what you can try to do is that find the dominant term from this expansion. Then try to show that the roots of this dominant term are close to that of the determinant. And here you need to carefully apply Rouché's theorem to actually claim that the roots of this dominant term are actually close to the roots of this determinant. And once you have shown that, then basically it follows by showing that this dominant term converges weakly to this limiting random analytic function. So these are the basic steps. Now how can we carry out these steps? So to do this formally, what we do is we expand this determinant and we write it as sum over pkz, where pkz is the homogeneous polynomial of degree k in the expansion of the determinant in the entries of En. So it means that you fix the size of x and y. Let's say you fix the size of x and y to be k. Then here you get a determinant of size k. And if you collect all those terms, that gives us pk. So what we do here is the following, that we show that for every z in RL, in any region that we choose, PLZ is a dominant term. Okay? And the rest of the sum of the rest of the terms is smaller than PLZ. Okay? And how do you show that? So there are two steps. First, you need to show that this sum over PKZ, where k is not equal to L, is little of this quantity. So here we use the second moment method. And to use the second moment method, you need some combinatorial techniques, and that will give you this result. Now you need to show that this is of the same order as this. So you need an upper bound as well as lower bound. So for the upper bound, you use again second moment method, and for lower bound, you need to use some anti-concentration techniques. So which I'm skipping here, and there actually we really use the fact that we have the entries are complex value random variables with bounded densities to get these anti-concentration bounds. Okay, and then once you have that, so this you can do for every fixed z, but this does not give you, or this does not allow you to apply Rouché's theorem. To apply Rouché's theorem, you need to show that this holds uniformly over. So let's say you want to apply Rouché's theorem for a certain domain. So this means you need to show that this holds for uniformly for all z over the boundary of the domain. So you need some stronger version of this, and this you can do by choosing some appropriate net of your domain. So this part I'm skipping. And once you have that, then you can combine these two steps, and then you can show the dominant term converges to this random analytic function, and then you'll be done. So I'll stop here.